Okay, this is the introduction for the E/m experiment, and essentially what we're going to be doing is we're going to be measuring the charge to mass ratio of the electron. Long time ago in the 1900s, this fellow by the name of John Thomson came up with this experiment when we were just learning about the electron and the fact that we have these particles in nature that have charge and fun stuff like that. So what he did was he had this little experiment, and I'm going to just make this guy a little bit bigger, where we had this tube, it's called a cathode ray tube, and we had this heater element, and essentially you get that really hot, and electrons kind of hop off of it. They hop off of the cathode, and then they are accelerated through some accelerating voltage such that they achieve some velocity. What we can kind of do is we can kind of say that the work that was done to them is going to be equal to the kinetic energy that they gain. So if I were to write this out, I would say that the work that is done to them is going to be equal to their kinetic energy. The work that is done, that's just going to be the charge that these guys have multiplied by their voltage, and then this is going to be equal to 1/2 mass velocity squared. So that's what this guy right down there kind of comes from. What we can then do is we can pass these through some plates, and these plates are going to have some voltage, and what we can say is that there's going to be some force acting on that guy. The amount of force is going to be equal to the charge times the electric field, or the charge times the voltage over the distance, recognizing that the electric field could be equal to that voltage divided by the distance. Note that this voltage right there is very different than the accelerating voltage. If we also had some magnetic field inside of there, then the magnetic field is going to act upon moving charges. And what we could essentially do is we could say that the magnetic force is going to be equal to the charge times the velocity times the voltage. It's going to look a whole awful lot like F is equal to QV crossed into B. And we can put all this together and say that the force is going to be that. If we were to try to balance these forces out, such that if we had some electron that's passing through these, then it's going to feel some charge or some force in this direction from the electric field and some force in this direction from the magnetic field, then we could say that the sum of the forces is equal to 0 if we're able to pass this beam straight through. That's all you're going to be doing in this guy, is you're going to be messing around with the accelerating voltage, hence you're going to be messing around with the speed of these guys, and then you're going to mess around with the deflection voltage and try to make the beam pass straight through. I'm just going to have you go ahead and do that for a couple of these guys and solve for the charge to mass ratio. It should be roughly this value right there. Note the unit is coulomb per kilogram, and I'm just going to have you do that for four different attempts. Now, you're going to go ahead and pop open the simulation. It's pretty straightforward. I'm going to get this guy right here, and you can just kind of mess around with these guys such that the beam is going to go straight through.